Hi everyone, my name is Leah Hess and I'm an undergraduate student in the Department of Chemistry at the University of Texas at Austin. My project this semester is titled The Molecular Modeling of Nanoparticle Stability in Organic Media. This project is sponsored by the online REU program at Texas A&M University and the National Science Foundation. My project mentor is Texas A&M's Dr. H.J. Su, and I would also like to thank Mingjun Zhao, Zuan Zhu, and Dr. Michael Demkovich for their help along the way. The ultimate goal of my project is to quantitatively model zirconium phosphate solvent interfaces. The use of zirconium phosphate nanoplatelets in a nanocomposite is a promising area of research due to zirconium phosphate's ease of synthesis, exceptional size control, and variety of size possibilities. When added to a polymer, these nanoplatelets can increase many desirable properties, such as mechanical strength, anti-flammability, and dimensional stability. To assist in the exfoliation of these nanoplatelets, organic modifiers can be added. Solvent, for example, can stabilize the exfoliation of zirconium phosphate in the presence of a polymer. However, currently only qualitative descriptions of this process exist. So that leads me to one of the ultimate goals of Dr. Su's group, quantitatively modeling the interactions of zirconium phosphate nanoplatelets with solvent in the presence of a surfactant. However, for the purposes of my project this semester, I begun by understanding solvent nanoplatelet interactions via the modeling of a sheet of graphene in a tunable solvent. I did this by using molecular dynamics software simulations to model graphene. So the first step was to create the graphene crystal structure in my LAMP simulation, and then I performed elastic constant calculations to validate the model and determine the relationships between defects and Young's modulus. The skills I've developed while building and performing my calculations on graphene sheets can be applied to other systems, hopefully in the future on the alpha zirconium phosphate I discussed earlier. And ideas such as parameterization and boundary conditions are necessary for every molecular dynamics task. And interpreting data in literature is also something that will be necessary for any future research. So to begin building my model, I had to gain an understanding of graphene itself. So graphene is a one-atom thick crystal of sp2 hybridized carbons arranged in a 2D honeycomb lattice shape, which you can see in the top right-hand corner. The bond distance between the carbons is 1.42 angstroms, and the unit cells have a lattice parameter of 2.46 angstroms. The interactions between the atoms are also important for getting accurate data, and I chose to use a potential called the adaptive intermolecular reactive empirical bond order, which is a mouthful, but it's a popular and widely used way to model carbon and hydrogen atoms. So since I'm using carbon in my graphene sheet, it was perfect for this model. So to calculate the atomic coordinates, I began by using MATLAB. I wanted to make a 10 by 10 unit cell sheet, which comes out to 24.6 angstroms by 42.6 angstroms, and I used the 4-atom unit cell and the trigonometric identities shown in this picture to generate the position of each of the 400 atoms in my sheet. I then wanted to visualize my model, so I used Atomi, which is a visualization tool. Atomi uses periodic boundary conditions in all directions, and your input must specify the number of the atoms, so in this case 400, the length of the sheet in each dimension in angstroms, the atomic mass of the atom, so in this case it's 12 for carbon, the atomic type, which you can label it as anything, but I chose the obvious label, which is C for carbon. The XYZ coordinates for every atom as a fraction of total length, so it's not a length across the sheet in angstroms, but a fraction of the dimension. And the velocities in each direction, and I didn't want anything to be moving, so in this case it was just 0 for X, Y, and Z. Next, I wanted to use my model for LAMPS calculations, so this involved editing the atomic positions as the code style is slightly different from the one I used for Atomi visualization. So for atomic position, I still needed to specify the number of atoms and the length in each dimension. The atom type in this case, however, is numerical, and my model only has one atom type, so the carbon atoms are all labeled with the number 1. The atomic mass is still the same, but now I needed to give each atom a unique label. So I have 400 atoms, and they were numbered 1 through 400. The biggest difference here between the atomic code is the coordinates. So LAMPS requires the positions in angstroms as opposed to the positions as a fraction of the total length. Also different is that no velocities needed to be specified for this. And then to actually perform calculations, LAMPS requires certain parameters to be input, so I had to specify the units used, and this is just a way to specify the units of all the input and output data. In this case, I used metal, which interprets mass as grams per mole, distance in angstroms, time in picoseconds, energy in electron volts, pressure in bars, temperature in kelvins, and then some other factors as well. The boundary conditions were also specified as periodic in X and Y and fixed in Z, as the stress for my purposes should not be applied in the Z direction. The atom style was input as atomic, which basically just affects what quantities are associated with each atom in the simulation and what is actually contributing to the measurements. And finally, I defined the potential as the potential I described before, the adaptive intermolecular reactive empirical bond order, and then I was ready to perform calculations. So for the elastic constant calculations, I used a code developed by Aidan Thompson of Sandia National Labs and tailored it to my specific material. So it utilized an NVT ensemble in a temperature of 0. And I was able to output the values shown in this material stiffness matrix that allowed for the calculations of Young's modulus, which is a measure of stress versus strain, as I'm sure you know, and Poisson's ratio, which is a measure of the relationship between strain in the loading direction and strain in the lateral direction. After getting a baseline Young's modulus for graphene, I introduced defects, specifically vacancies, and measured their effect on the Young's modulus. To mitigate some of the error that may come with the sheet size that I used percent vacancy instead of deleting a specific number of carbon atoms. This was done using the delete atoms porosity function, which deletes a certain percentage of random atoms. And here I have some examples of what vacancies might look like. So here are the elastic constant results. For perfect graphene with no vacancies, I found a Young's modulus of 0.88242 terapascals and a Poisson's ratio of 0.31586. In the chart on the bottom of the page, I've compiled some literature values that utilize different methodologies and or potentials to find Young's modulus. And so as you can see, my result is in the acceptable range compared to the ones you see here, but differs slightly from the experimental value of 1. And I expected my value to be very similar to the value highlighted here in gray, as I used a very similar methodology in my simulation. However, they did use a different potential, which could explain the differences. So here are the results for the effects of vacancies on Young's modulus. So as you can see, Young's modulus decreases as vacancy increases, and there's almost a linear relationship with increasing vacancy percent. So as I mentioned on the previous slides, the various modeling systems and potentials have an effect on the measurement. This model could have been made inaccurate by a variety of factors, including size, hybridization, and defect type. So like I said, carbon can exist in sp, sp2, and sp3 hybridizations. My model assumed only sp2 configurations. Planar carbon also has many allotropes, such as PSI graphene, shown in the bottom right. And there are also different types of defects. My model assumed simply just a deletion of carbon atoms, but in reality, vacancies can affect the structure in different ways. For example, in the bottom left, I have a picture of a stone walls defect. So to continue exploring this model, I could look at the effect of different factors on the elastic constants or the energy of graphene. So for example, I've seen other papers, whether it be graphene or other materials, use variables such as temperature, types of defects, size, potential, and the number of sheets. And the skills I've learned by modeling graphene are also helpful for the modeling of other materials, and research directions include shifting to hybrid materials where potentials and interactions are more complex. And ultimately, with more practice, this would allow for an investigation of the alpha zirconium phosphate material and other nanoparticles. Thank you very much for your time.